Welcome to the second module of the Securium Bootcamp. In this module, we'll be touching upon 101 basic concepts related to the Solidity language. To set the context and expectations from this module and from this video presentation specifically, the focus will be on looking at the high-level concepts related to Solidity basics. This content is adapted in many cases verbatim from the official documentation of the Solidity language. And the focus is going to be on reading Solidity code from the perspective of evaluating security of smart contracts written in Solidity. The focus is not going to be on writing Solidity code. So if you're really interested in learning how to write smart contracts in Solidity, then there are many online resources, fantastic courses and other resources online. So I would encourage you to take a look at those and maybe even spin up your favorite IDE and code up some basic examples related to each of these concepts. Some of these illustrative examples are given in the Solidity documentation as well. So let's dive in. Solidity is a high-level language for writing smart contracts on Ethereum. It targets the underlying Ethereum virtual machine that's fundamental to how Ethereum works. Solidity was proposed in 2014 by Gavin Wood, was later developed and is continued to be developed by Ethereum's Solidity team, led by Dr. Christian Riedwiesner, Alex Beregzasi, and others. And given that Solidity is so commonly used and there are so few alternatives to high-level languages on Ethereum, this has become really a fundamental pillar to smart contracts on Ethereum and therefore the security of smart contracts on Ethereum. If you look at what other high-level languages have influenced Solidity, it's mainly influenced by C++, a bit from Python, and some of the early motivation was also from JavaScript. A lot of the syntax and the object-oriented programming concepts we see in Solidity are heavily influenced by C++. The use of Solidity's modifiers, multiple inheritance, C3 linearization, and the use of the super keyword are from Python. And early on, there were influences from JavaScript as well, things like function level scoping, the use of var keyword were taken from JavaScript, but those influences have significantly been reduced since version 0.4.0. So again, Solidity is really a fundamental pillar of smart contracts on Ethereum and therefore the security of smart contracts on Ethereum. There are very few alternatives. Viper is one of those languages that is just started to catch up with some of the high profile projects on Ethereum. There are many other languages that are being researched as well, but to a great extent, the maturity of the language, the tool chains built around the language, Solidity is by far the most widely used. So it really becomes critical that in order to evaluate security of smart contracts, we understand the syntax, semantics, the pitfalls, and various other aspects related to Solidity. What are the features of the Solidity language, the language characteristics at a very high level? Solidity is what is known as a curly bracket language. It means that curly brackets are used to group together statements in Solidity within a particular scope. Solidity is also an object-oriented language. So if you have learned any of the other object-oriented languages, you will find a lot of similarities, especially with C++. Solidity is also statically typed. It means that the types of variables defined in Solidity are static and defined at compile time. This is in contrast to some of the dynamically typed languages that you might have learned. Because of object-oriented programming, there is the use of inheritance in Solidity. There is code reuse, code modularity in the form of libraries that is supported. There are also user-defined types, and this really makes Solidity a fully featured high-level language that lets us define complex logic in smart contracts to really leverage all the underlying features of the Ethereum virtual machine. How does the physical layout of a smart contract written in Solidity look like? So this is important to the readability aspect of the file, the maintainability aspect of the smart contract in the context of the project itself. Solidity source file can contain an arbitrary number of various directives and primitives. These include the pragma and the import directives, the declarations of structs, enums, and contract definitions. And every contract can itself contain structures, enums, state variables, events, errors, modifiers, constructor, and various functions that define the various functionalities that are implemented by the smart contract. So this physical layout is something that is specific to the syntax of Solidity. It is again a best practice. The language itself, the compiler itself, supports the developer to jumble up a lot of these constructs in different ways. But when it comes to helping with readability or maintainability aspect, which significantly influence the security of the smart contract, this order is what is considered as a best practice. So this is something that you will commonly see when you evaluate smart contracts in Solidity. There might be cases where some of these are out of order from what is considered as best practice, but something to keep in mind. One of the things that you will often see specified at the top of every Solidity file is what is known as the SPDX license identifier. SPDX stands for Software Package Data Exchange. In the case of Solidity, this is really a comment that indicates its license, and it is specified as a best practice to be at the top of every file. An example looks like this, where it will say SPDX license identifier followed by the specific license that the smart contract developer intends for this particular smart contract. And this identifier, the license, is included by the compiler in the bytecode metadata that is generated so that this aspect really becomes machine readable. The pragma keyword in Solidity is used to enable certain compiler features or compiler checks. An example looks something like this. It can say pragma solidity caret 0.8.0, and we'll see what that means in the forthcoming slides. But at a high level, there are two types of pragmas. The first kind specifies the version, and there are two types of versions that can be specified: the version of the compiler, so Solidity compiler itself, and the version of what is known as an ABI coder. And this could be either version 1 or version 2. And that specific version is declared by the pragma directive. The second pragma directive helps the developer to specify the use of any experimental features in Solidity. And as of now, this is really one experimental feature known as the SMT checker. And what needs to be kept in mind with the pragma directives is that they are local to the files where they're specified. So if you have a Solidity file that imports other files, the pragmas from the imported files do not automatically carry over to the file that is of concern. Let's now take a look at the version pragma as it applies to the Solidity compiler version, how it is specified, what the format is, what the different formats are, and what it does. The version pragma really indicates the specific Solidity compiler version that the developer expects to be used for that source file. And it looks like pragma solidity x.y.z, where x, y, and z are numerals that specify that compiler version. What this does is it does not change the version of the compiler used. It does not enable, disable any features of the compiler. All it does is it just instructs the compiler at compilation time to check whether its version matches the one specified by the developer as part of this pragma. And this could be of several formats. It could be a very simple format, a complex one, or even a floating one, which has some security implications. The latest Solidity compiler versions as of now are in the 0.8 range. A different Z in the pragma directive, if you look at x.y.z, a different Z indicates bug fixes and a different Y indicates breaking changes between the compiler versions. So if we have compiler versions in the 0.5 range, and then if you look at the 0.6 range, it means that the 0.6.z range have at least one or more breaking changes compared to the previous versions. Now compare and contrast this with the semantic versioning or semver that has a major, minor, patch versioning that we see with many software products. That'll be an interesting exercise. A floating pragma is a pragma that has a caret symbol prefixed to x.y.z in the directive, and this indicates that the contract can be compiled with versions starting with x.y.z all the way until x.y+1.z. So specifically, as an example, if we have a pragma directive, pragma solidity caret 0.8.3, then it indicates that the source file can be compiled with any compiler version starting from 0.8.3, going to 0.8.4, 0.8.5, and whatever else has been released, but not 0.9.c. So the transition from 0.8 to 0.9 is what is allowed or prevented by this floating pragma. So this really allows the developer to specify a range of compiler versions that can be used with this particular contract, and that has some security implications. Similar to the floating pragma, a range of compiler versions can be indicated with a complex pragma, where you have greater than or equal to, less than or equal to symbols that are used to combine multiple versions of the Solidity compiler. Now this affects the compiler version, which in turn brings in different features that are implemented by that compiler version. Some of those could be security features, some of those can be security bug fixes, optimizations, and all these aspects really affect the security posture of the bytecode that is generated from this particular smart contract. So that's the context in which this pragma directive becomes relevant as we evaluate the security of smart contracts. The second version pragma directive is what applies to the ABI Coder. Recall that ABI refers to the application binary interface. So this ABI Coder pragma directive allows the developer to specify the choice between version 1 or version 2. The newer version 2 was considered experimental for a while, but is now activated by default. and this allows the encoding decoding of nested arrays and structs. And we'll take a look at these data types in the later part of this module. And V2 is a strict superset of version 1. And what this means is that contracts that use it can interact with other contracts that do not use it without any concern or limitations. This pragma also applies to the code defined in the file where it is activated, regardless of where that code ends up eventually. And what this means is that a contract whose file is using ABI Coder V1 can still contain code that uses version 2 by inheriting it from another contract. So given that this version pragma that specifies the ABI Coder affects encoding, decoding, and really the optimizations, it does have certain security implications. The next version pragma is the experimental pragma. And this is used to specify features that are considered as experimental as of that point in time. These features are not enabled by default and have to be explicitly specified as part of this pragma directive within every file where that is required. As of now, there is one experimental feature that is known as SMT checker. SMT stands for Satisfiability Modulo Theory. This is an approach to formal verification, and in this case of Solidity, it is used to implement safety checks by what is known as querying an SMT solver. There are various security checks, safety checks performed by the SMT checker. The first one is where it uses the require and assert statements that are included as part of the smart contract. The checker considers all the required statements specified as assumptions by the developer, and it tries to prove that the conditions inside the assert statements are true. If a failure can be established, then the checker provides what is known as a counterexample that shows the user how this assertion can fail. There are various other checks that have been added to the SMT checker over time. These include the arithmetic overflow underflow, division by zero, unreachable code, and so on. So SMT checker is a critical security feature that comes packaged as part of the Solidity. It's implemented in the compiler itself. And at a higher level, formal verification is considered as really a key area, a fundamental part of programming languages security. So we can imagine that this particular pragma directive specific to the SMT checker affects the security and optimizations of the smart contracts that use this feature. Let's now take a look at the import directives. These directives, import statements, are similar to JavaScript, where the format is really import file name, and they help to modularize your code, split what might become a large monolithic code base into multiple components, modules, and import them wherever they are required. So this helps developers to reuse the code, and this again affects not only the readability aspect. When you compare and contrast a piece of monolithic code that is hundreds or thousands of lines versus modular code where they're separated out into independent self-contained modules and used only where required. So that obviously affects the readability, but it has implications to security as well, to optimizations as well, and we'll talk about those concepts when we start evaluating security. Programming languages support comments, different types of comments, that can be used within the code. In the case of Solidity, it supports single line comments and multi-line comments as shown here. And these comments are recommended, are used as inline documentation of what the contracts are supposed to do, what the functions, variables, expressions, various control and data flow, what they're expected to do as per the specification and what is really implemented. They can also be used to specify certain assumptions that the developer is making in the implementation. And they can also represent some of the invariants that need to be maintained. So these comments really become a critical part of documentation that is included or encapsulated within the code itself. And they affect the readability of the code to a great extent, maintainability as well. So you can imagine that comments really become critical when we start talking about evaluating the security of smart contracts. So when we start reading manually the smart contracts, then these comments really give us a lot of vital clues as to what the developer intended, be it assumptions, be it invariants, or be it just information related to the various syntax or the semantics itself. Solidity also supports a special type of comment called NatSpec, which really stands for Ethereum Natural Language Specification Format. These are specialized comments that are again specific to Solidity, specific to Ethereum in this case. They are written with a triple slash or a double asterisk block directly above the function declaration or statements that are relevant to the NatSpec comments. These NatSpec comments come in many different types. There are many different tags, such as title that describes the contract or the interface, author that specifies the developer who is authoring this contract, the notice tag that explains to an end user what this particular contract or function does, dev tag that is really directed towards the developer for any extra details implementation related. There are also specific tags related to function parameters, the return variable, and so on. These NatSpec comments are really meant to automatically generate JSON documentation for both developers as well as users. And there are some very interesting use cases of these NatSpec comments as well. So these are again comments that you will see inlined when you look at Solidity smart contracts. They provide a lot of valuable information that the developer intended for all these various aspects of parameters, returns, contracts, and so on. So these comments also form an important piece of the tool set that helps evaluate smart contract security, as we'll see later on. Smart contracts, or simply contracts, are really fundamental to what Ethereum is all about. And conceptually, contracts are very similar to the concept of classes in object-oriented programming. And that's because they encapsulate state in the form of variables and logic that allow one to modify that state in the form of functions. And these contracts can inherit from other contracts, they can interact with other contracts, and really support a very rich environment where one can specify different types of interactions between these components. So these are really fundamental primitive of Ethereum, and we'll take a deeper dive into the many components and the many aspects of smart contracts in this module. So what do these contracts contain? They can contain different components. They include structures, enums, state variables, events, errors, modifiers, constructor, and various functions. Some of these concepts are familiar or should be familiar to you from other programming languages, but there are also some very Ethereum specific aspects here, such as those related to state variables or events or something that's specific to Solidity in the case of modifiers. And these contracts can come in different types. They can be what are known as vanilla contracts, or they could be libraries or even interfaces. And we'll take a look at all these different components and aspects in this module. State variables are a critical component of smart contracts. These are variables that can be accessed by all the contract functions, and the data location where these state variables are stored is what is known as the contract storage. If you recall from the Ethereum module, EVM has multiple components. It has the stack, it has call data, then it has the volatile memory, and finally it has the non-volatile storage. This non-volatile storage is where the state variables are stored. And the reason for that is the state variables need to persist across transactions that affect the contract state. State variables have a concept of visibility in Solidity. These visibility specifiers really indicate who can see these state variables and who can access them. There are three such visibility specifiers: public, internal, or private. Public state variables are part of the contract interface, and they can be accessed either internally from within the contract or from outside the contract via messages. And for such public state variables, an automatic getter function is generated by the compiler. This function can be used to access the values of these public state variables. The second visibility specifier is internal. Internal state variables can be accessed only internally from within the current contract or contracts deriving from this contract. The third one is private visibility. Private visibility state variables can be accessed only from within the contract they are defined in, and not even from the contracts that are derived from it. So these visibility specifiers are interesting from a security perspective because although these seem to give an impression that certain state variables are private in sort of a privacy centric manner, everything that is within a contract is really visible to all the observers external to the blockchain. And the private visibility specifier really makes these variables private to the contract and prevents only other contracts from reading these variables on chain. But all these variables can be looked at, can be queried via different interfaces. State variables also have a concept of mutability. This really indicates when can these state variables be modified and what are the rules for those modifications. There are two such specifiers. They are constant and immutable. Constant state variables are fixed at compile time. This essentially means that these variables have a value that is the same as when they were declared for the life of the contract. And there are certain rules for what expressions can be used for defining these constant variables within the contract. Immutable variables, on the other hand, are fixed at construction time. This means that they can be assigned values within the constructor of the contract or at the point of declaration. They cannot be read during construction time, and they can only be assigned once. These properties of constant and immutable state variables allow the Solidity compiler to prevent reserving any storage slot for these variables, and this property makes these variables storage and gas efficient. Let's talk a bit about the mutability aspect that we just talked about, and the implications on gas usage. Compared to regular state variables, the gas costs of constant and immutable variables are lower. And the reason for this is because, as we just saw, for a constant variable, the expression that is assigned to it is copied to all the places where it is accessed within the contract. And it's also re-evaluated each time. This aspect allows the Solidity compiler to make some local optimizations wherever constant variables are used. And for immutable state variables, they're evaluated only once at construction time, and then their value that's just evaluated is copied to all the places in the code where they're used. Now, for these immutable variables, 32 bytes are reserved even if they require fewer bytes. And due to this aspect, the constant variables can sometimes be cheaper than the immutable ones. And for now, the only supported types for these variables are strings and value types. Functions. Functions are the executable units of code. And in the case of Solidity, these functions are usually defined inside a smart contract, but they can also be defined outside of the contracts, in which case they are really specified at a file level, and such functions are referred to as free functions. And these functions, if you recollect, are really what allow modifications to the state that is encapsulated as part of the contract. And this is really how logic manifests itself within the smart contracts, and the state transitions from one initial state to the modified state as a result of any of the transactions or messages that interact with this smart contract. Functions typically specify parameters. These are treated, declared just like variables within the function, and parameters are really how the caller of the function sends in data into the function for it to work on. And these are used and assigned very similar to local variables within the function. And the nomenclature is, or the terminology is, that the function specifies the parameter and the caller really sends in arguments that get assigned to these parameters in the context of the function and let it work on those arguments and do something with them.